Welcome everybody. Today's lesson is all about inverses. For today's lesson, there are three major points of emphasis. The first is that to find an inverse, I simply need to switch x and y. So for our first one, it says if a rule for f exists, a rule for g can be found by switching x and y in the rule for f. In other words, we're going to switch x and y. The second is in regards to the graph. It says that the graph is the reflection image of the graph of f over the line with the equation y equals x. Essentially, to find the graph of the inverse, I will reflect over the line y equals x. Now, you may forget what that looks like. If I'm given the coordinate plane, the graph of y equals x is this diagonal line here. Okay, so for example, if I have the graph of a parabola here, when I reflect it over this line, it'll be something like this over here, simply reflecting each of my points over that line, y equals x. And the last piece that we'll talk about is in regards to the domain and range. And since the x and y values get flipped, the domain and range switch as well. All right. One of the good ways to determine whether or not an inverse is a function is using the horizontal line test. And we'll talk about that more as we get into the notes, but if you remember, the vertical line test asks me to draw vertical lines through a graph. If that line touches only once, this is a function. Now, to test whether the inverse of a function is a function, I use the horizontal line test. And as you've guessed it, I'm going to draw horizontal lines through my graph. The same rules apply. If that horizontal line touches my graph more than once, which it does in this situation, then my inverse is not a function. That information will come in handy as the notes go on. Alright, let's look at example 1 where I'm given a relation and only x and y coordinates. To find the inverse, I simply switch the x and the y coordinates. So, the inverse, denoted with a -1, is 5, -2 for my first point, 7, -1 for my second point, 3, 0, 7, 1, and 1, 2. Now, is this a function? Well, it's not a function because I have one x value that maps to two different y values. So this is something important to keep in mind as we continue to talk about inverses. Looking at example 2, we're going to start looking at the graphs, talking about the domain and range and determining whether or not this inverse is a function. So we're going to look at the graph y equals -2x squared. The domain is the set of all real numbers. So what's the equation for the inverse of the function? As we mentioned at the beginning, to find the inverse, I switch my x and y values. So I rewrite what I've got as x equals -2y squared. Now, I'm going to want to solve for y so we can see the inverse of the original function. To solve for y, I need to start moving everything away from it, so I'll divide here by -2. So I've got x over -2 equals y squared. And then to finish it off, I'll take the square root of both sides. So y equals the square root of x over negative 2. There you have the inverse of that function. Now, let's look at how to graph. The easiest way to graph is to make a table. Okay, I've got my x and my y. Let's look at the original function of y equals negative 2x squared. If I plug in some familiar points, negative 2, negative 1, 0, 1, and 2, I end up getting negative 8 for y, negative 2, 0, and then those values will repeat, negative 2 and negative 8. As you suspected, we will end up with an upside down parabola with my vertex at 0, 0. So I move over to negative 2, down to negative 8. I've got negative 1, negative 2. And I'll finish off my graph here. Connect the dots to form a nice parabola. All right. Now, remember, to find the inverse, I simply need to switch the x and the y values. So I switch. Looking at my table, I'm just flipping the values for x and y. And as mentioned earlier, this will be a reflection over the line y equals x. So there's that line y equals x. My new graph turns out is the exact reflection. So I've got to go over negative 2, negative 1, over negative 8, negative 2, and the same thing on the other side. To form my nice parabola. Now, is my inverse a function? For part C, is my inverse a function? No, it fails the horizontal line test. If I look at the original function shown down here, if I draw my horizontal lines through there, you can see that I'm intersecting in more than one spot. That's why it fails the horizontal line test. Alright, now it's time for you to do a little work. Try the on your own problem and then check your answer. You should have, for part A, switched the x and the y value. So x equals 3y plus 2. When you solve for y, you have x minus 2 equals 3y. Both sides get divided by 3, so y equals x minus 2 over 3. Is the inverse a function? Well, we can think of this in several ways. We can look at the original graph, which is a line with my intercept at 2. If I use the horizontal line test, I'll see that it only intersects in one spot, so yes, inverse is a function. Hopefully we're catching on. Let's flip to the back. Alright, we're going to start using that horizontal line test and again talking about some domain and ranges. So for the first one, is the inverse of each function a function? For part 1, oops, my horizontal lines aren't so horizontal. I'll see that for each line it intersects in only one spot. So for my first graph, yes, the inverse is a function. For graph number 2, using the horizontal line test, boom, boom, boom. I've connected twice with my horizontal lines, so no, the inverse is not a function. How about the domain and range? All right, for the first one, my domain, and let's clean it up a little bit. My domain, you can see, it'll expand all the way. It'll keep expanding all the way negative, keep expanding all the way positive. So my domain is all real numbers. My range, because that graph extends all the way positive and negative, will be all real numbers. For graph number 2, and let's clean this one up a little bit, you can see that my domain, the graph extends in both directions along the x-axis. So my domain is all real numbers. However, my range is limited. It does not go above 2. So my range is all values less than or equal to 2. Now, when referring to the inverse, you'll remember I simply switch the domain and range. For the first graph, that doesn't really affect anything. The domain is still all real numbers. The range is still all real numbers. Now, for graph 2, my domain is all values greater than, or excuse me, less than or equal to 2, and my range values are all real numbers. All right, moving on. Example number 4 asks us again to write a rule for the inverse of h. Now, h is a function, and I'll use the same method of switching x and y to determine my rule. So here's how it works. You remember this is mapping notation, and I can simply write a y in here to replace all of that. Okay, so for the purposes of this problem, I replace my mapping notation with a y. Now I'm going to switch my x and y and solve for y. So I get x equals 4y plus 7 minus 3 over 2. Now I'll solve for y and my rule will be complete. I'm going to multiply both sides by 2. So 2x equals, I'm going to simplify the top here, 4y plus 28 minus 3. Simplify again. I've got 4y plus 25. I need to subtract 25 from both sides. So 2x minus 25 equals 4y, and my last step will be to divide by 4. So my final rule is y equals 1/2 x minus 25 over 4. That's the rule for the inverse of this function. The domain and range have been flipped. The graph has been reflected over the line y equals x. There you have it. That's the concept of inverse functions. Tomorrow in class we'll get into example number 5 and talk about more ways that this can be applied.
The combination D-E-F is who I am, is what I do, and I was gonna lay it down for you. I tried to focus my attention